Okay, welcome to this session where we'll be talking about Thevenin Theorem. Okay, so this Thevenin Theorem will be applied to the following circuits. We'll take a basic circuit. We will have the input here. That is input, AC input. We'll take, for example, 2.5 volt peak, 10 kilohertz as a supply. Since this one it's going to be our reference, so we'll make it 0 degree as a phase shift for that source. This will be connected to the first resistor, R1. We'll take R1 to be 1.2 kilo ohm, connected to inductor in series like this, with a value of 10 millihenry, and parallel branch, which is a resistive load, resistive branch here, R2, which is 3.3 kilo ohm. Okay, so this circuit will be supplying a load, and we call this load RL, 1 kilo ohm. We'll take 1 kilo ohm for this exercise. Now, to verify this Thevenin theorem, first of all, let's take the original circuit. Let's call this one original circuit, and try to find the current flowing through this load here. Let's say I original, O for original, so IO. Okay. To do this, so we do it practically. We connect the circuit as it is, okay, with our oscilloscope, the Tektronix, the one we have. We connect the channel 1 to this point here in order to display our V input, sine wave, okay, and the channel here at this point, channel 2, where we can display V across RL. So it can be with the phase shift, for example, something like this, and smaller, of course, sorry. Anyway, something like this. This will be V source, Vs, and this will represent VR load. From this VR load, okay, if we are able to find the V max of that signal, so VR load max or peak, we can divide this by our R load, so we can easily find the peak value of this current I original peak. Okay, now to represent this current here, I, in phasor form, we need to find the phase shift. So between those two signals, also we can use the cursors here, and we can find delta t. That delta t will be the phase shift in microseconds, for example. We will multiply this to by 360 and by our frequency, which is 10 kilohertz for our case. So this will give us the theta for I original in degree. Okay. So now, mounting the circuit as it is, we can find the current I naught or I original, okay, which is I original peak with the angle of that I original peak in degree. So that's the final value that we need to keep for this original circuit. Okay, now to verify the theorem Thevenin, we go by steps. Let's say, for example, step number 1, we need to find Vth, okay, because by the end we want to have a circuit which will be represented by Vth and Zth, two elements like this, source and its impedance, with its impedance, and we connect back the load. So Vth, how to find it practically? We remove the load, so we'll end up with a circuit like this. Okay, practically no need to remove this inductor, even if there is no current flowing through it. We keep it like that, say, connected to the circuit. So Vth should be at this point here, this terminal, that is Vth. And since there is no current flowing through this inductor because the circuit is open, so Vth will be seen also at this point here. It will be same as this point. Let's call this one here Va, for example. Okay, if we come to this, the voltage across this inductor, and we call it a VL for inductor. So basically what is VL? VL will be the high potential, which is VA, minus the low potential, which is Vth. Now, since XL times 0 will be 0, that is VL, so VL will be 0 equals VA minus Vth. Therefore, the Vth will be equal VA. That's why I told you this Vth here. Okay, this value of Vth on this point will be seen here. It's similar to that point. Okay, so this is R1 and R2, and this is Vs. Okay, it's easy here. We see that those two resistors, they will share the value common, or the source, the value of this source here connected to them, and this is what we call voltage divider. So VA, which is Vth, according to this demonstration here, will be equal V source. That's a rule for this voltage divider, multiplied by R2 divided by R1 plus R2. So this, it's a ratio, it's unitless. Ohm by ohm will be simplified, so it's only a ratio constant. And since this constant, it's composed by resistors, so there's no phase shift will be created between the input Vs and Va or Vth. Okay, the only difference will be between Vs and Vth is the amplitude of both of them. Vs, of course, will be in terms of amplitude or max, will be bigger than V across this load or Vth itself. Since R2 will be having a drop, voltage drop across this R1, sorry. So this voltage drop will be deducted from Vmax of this Vs, will be our Vmax across this point here, across this resistor, or at this node Va. Okay, so once you do the plot, if we connect, we keep connecting our channel 1 here and channel 2, this point here. So basically what we have done, we kept the original as it is, the original circuit as it is. We took off only the resistor. You can take one terminal of this resistor, or take off all the resistor, both terminals, and you end up to this one with its channels connected to it and so on. So the oscilloscope will display again Vs and Vth, which is in phase, but with the small value in terms of Vpeak. So this here will be Vth. So its maximum here represents Vth max. So Vth, okay, will be equal Vth max or peak. The angle will be 0. So this will be our reference now for the Thevenin circuit, equivalent circuit. Okay, so that's Vth. Step number 2, we need to find now Zth. To find Zth, let's consider our redraw here the circuit again. Inductor. So Vth, I mean, this Thevenin theorem says what in terms of finding this Zth? We have to replace all voltage sources by short circuit. Replace, not make short circuit. We have to take off this voltage here source, replace it by short circuit. And if we have in our circuit anywhere here, if we have open another for example, another voltage source, we have to replace it by short circuit. If we have anywhere a current source, we have to replace it by open circuit. So this will be replaced by short circuit, and we'll be having this circuit by the end with the inductor here. Okay, so this is our circuit, and we are ready now to find the Z Thevenin. This is R1, R2, and L. Now, if we were given like a resistor, for example, okay, and we were asked to find the value of the resistor without using this color coding technique, or without using multimeter or ohmmeter to measure the value of this. So the only way to use that is to supply, because the Ohm's law says what? V equals Ri. So R will be V over I. And to find the value of R, we should have a V somewhere across that resistor, of course, and the current flowing through that resistor. So the only way to do it is to supply that resistor with either DC or AC source, and we'll try to measure. This will be given by us, so we know exactly the value of that one. Can be 1, can be 10 volts, can be whatever we have as a voltage available in our power supply. Let's say, for example, we have, like, for example, 2 volts peak if we use AC voltage. The current here, if we put here a meter, we can measure the RMS value flowing through this resistor. So 2 volt peak divided by root of 2, okay, to convert this peak to RMS. Divide this by the value shown by this ammeter. Example, for just example, let's say 1 milliamp. So here we can find, if we do the division here, will be this value in kilo ohm. So X kilo ohm. So this is how we can measure that resistor, or we can find the value of the resistor by supplying it by source, voltage source, and measuring the current flowing through it, and we can apply this Ohm's law, and we can find our resistor. So the same technique should be used for our circuit. So let's imagine, for example, that this one here is a box or black box where we don't know what is exactly inside this box. Can be resistive load, can be inductive, can be a capacitive network here. We don't know. How to know that is to supply this by AC source. Okay, since we don't know, so absolutely we have to use AC. We don't use DC here, so AC only. And that AC will supply current this way, say I. That current will flow, will circulate inside this box, and will come to this. Okay, okay, 1 second, sorry. Okay, sorry. So okay, we're supplying this black box by a voltage source, and this current will flow inside this black box, and will come back here through this wire. Okay, now we know exactly what is the volt that we are supplying. Let's say, for example, 2 volt peak. Let's say 1 kilohertz, for example, or 10 kilohertz. Okay, this will be our reference, so 0 degree. Now the only thing to be measured is the current. Okay, because we can, if you can find the current and you have a V divided by this current, so will give us, this is theta of this current here. We can find exactly this Z. So now the only way to do this and measure that current is, if we don't have a current probe, for example, only voltage probe. For our case, we are using this Tektronix. So here, what you have to do, you have to add the resistor here in series with that in this section here exactly. Okay, since our probes should be grounded, so we use the resistor in this section here in the return of that current. The value of this resistor should be selected in order to not affect the internal resistor of this box. So it's better to make it like too small, can be 10, can be 50 ohm, for example. Okay, and so this for sure will not affect the behavior of our box here. And now, since we have this, we can make two channels here. Channel 1 connected to this point in order to display V source, and another channel in this point here, channel number 2, with its ground will be connected to this part ground here. Same thing for channel number 1. The ground will be grounded here. If you are using Tektronix, the one we use, they have like 4 channels. 2 channels they are grounded. So if you ground the channel 1, no need to ground channel number 2, the probe number 2. Otherwise, just to be sure, and we ground both of them, and that's it. So this will be given by channel 2, channel 3, channel 1 here. Channel 2 will give another voltage across this resistor here. Now, if we combine them in the same graph, we'll be having something like this. This is a Vs, that's Vs here, channel 1. And the other V will be phase shifted. If it's not phase shifted, if suddenly we have Vs and V channel 1 and V channel 2, they are in phase, means phase shift equals 0. So we know exactly that whatever is here as network, in terms of connection like series or parallel, they are all of the elements here, they are resistive elements or resistors, because the resistor doesn't create any phase shift in our circuit. If we have a phase shift, it depends leading or lagging. That will give us that an idea that this circuit or black box behave either inductively or capacitively, let's say with the capacitive load or behavior or inductive behavior inside this box. So here, that's V channel 2. If we take the max of this V channel 2 and divide that, so V max or peak for channel number 2 divided by 50 ohm, because this resistor will give us the image of the current. It's like our mirror to see the current flowing inside this box here and coming back to our source. So V peak of this channel number 2 divided by 50, this will give me I peak, which is this one. Okay, now okay, so this is I peak. We need the phase for that I. Okay, that is the phase shift between this source and that voltage. The voltage is the image of the current here inside this circuit. So that delta T, the new one, we multiply this by 360 and by our 10 kilohertz, the frequency is set here for this source, will give us this data here. So Z will be equal okay. So this Z will be this V here, 2 volt, for example, 0 degree divided by this. So V with its angle 0 divided by this V peak of channel number 2 divided by 50 ohms with its angle here. That angle theta I. So the result will be Z, okay, magnitude here, or this V divided by this here, with another angle which should be negative theta I. Okay. So now, if we convert that Z, say Z, say like this, and the angle will be negative I, theta I. So we convert this one to triangular will form. So Z will be our Z Thevenin now, will be represented by real parts, okay, minus J and imaginary parts here. Okay, so this R will, this real part will represent our R Thevenin. Okay, and imaginary part will be our X. Okay, and since here in our circuit we don't have any capacitor, so obviously this one will be inductive, so XL. Okay, now this R here, if you have a value like, for example, let's say 1055, for example, ohm. So if we don't have nominal value or standard value like this, so we can use variable resistor to fix that value, to fix it to this value here. So this value coming from your calculation, you should take this XL divided by 2 pi f, will give us our L to be used in our circuit. And since we have only one inductor in our circuit, so it comes back to the same inductor we used before in our original circuit, okay, 10 millihenry. Okay, so this is our Z Thevenin. Okay, so now what you have to do, the last step, let's say in step number 3, okay, we construct our final or equivalent circuit. This is a Vth, and we have to set our function generator to V maximum, V Thevenin peak, the one calculated before or found before in our previously here. So this V Thevenin here with that peak, the measured one. Okay, the angle will be 0, of course, and the frequency will be 10 kilohertz. Okay, since we started with 10 kilohertz as a frequency for our first original circuit, so the frequency will not be changed, 10 kilohertz. Okay, now variable resistor to represent that R Thevenin, inductor L. Okay, and now we put back our load. This is RL, the 1 kilo ohm, okay, load, and we do same thing, 2 channels, channel 1 here, channel number 2 this side. Both of them, they will show two signals, sorry, okay, and shifted, of course, since we have L in our circuit. This here will give us, this is channel number 2. Peak of that divided by 1 kilo ohm will give us I peak, and its angle, which is this theta here. So we should end up with the same value found at the beginning, which is this value here, this one. So those are the steps to be used in order, practically, in order to find Vth and Zth here, and verify the Thevenin theorem. Thank you.